We now continue with Dr. Charles Gerba, who was introduced yesterday by Liz Scott. Let me remind you, he is with the Department of Soil, Water, and Environmental Science at the University of Arizona in Tucson. He has an active research laboratory and team, also very involved with their School of Agriculture. And he will continue this discussion of risk paradigms, new ways of looking at cleaning, and in this case, health, the assessment to set cleaning goals for norovirus. Please again welcome Chuck Gerba.
Well, thank you. To hopefully give you an opportunity to show how risk assessment might be used to try to achieve some of the goals this organization will be focused on. As a preface to me talking, a lot of the efforts I'm going to talk to you about are part of a center that was funded by the Department of Homeland Security and the Environmental Protection Agency, with the Michigan State University being the lead university, and my university and several others around the country being involved. The focus of that center was, one of the main focuses is to look at bioterrorist agents and try to assess the risk if they were released in a room like this or in a facility. A lot of other aspects of that center goes into drinking water and other areas. So I think some of the efforts of that center is focused on some of your concerns. What I'm going to do is show you one of the efforts that the center has been focusing on and looking at the applicability of microbial risk assessment in indoor environments and clean. Because one of the issues with a bioterrorist event is how do we know it's safe to go back in the building? And it becomes a very critical issue there, how clean is clean, because you're looking at agents with very high mortality. We're looking at agents with maybe 90% or more mortality. So it becomes a very critical issue, not about running to the toilet more often. It's about, dragging the corpse out. So it becomes a much more critical issue to look at. But how do you get a handle on that, and how do you develop the science? I'm going to try to review this a little bit again, because this is one of the issues we're faced with in bioterrorist events, is how clean is clean? How safe do we have to make it, and how do we know it's safe again? One of the things a little bit, again, on introduction here, is we're looking at the issue here, I think, of safety of it. No human activity, of course, is risk-free, and they have to accept that with microbial risk assessment, because what I'm going to try to do is put a number on that risk, try to be quantitative. You can be qualitative in risk assessment, say this is safe, it's safer. But in the microbial realm, we try to develop the area of quantitative microbial assessment so we can compare numerically, at least within a range of uncertainty that we define, what is safe. One of the other things is there's more concern about involuntary risks. For example, driving a car rather than a pathogen in food. People feel they have control over driving a car, and so they're willing to accept much higher risks than flying in an airplane, which is far safer. But there's a perception you're in control. The same thing with drinking water and food. That's delivered to people, or they purchase at a store. They don't feel like they have really control over the safety of that food as much. So they will perceive these risks in different ways, and they will demand more of agencies like the federal government. They want those risks much lower. Basically, most people, when it comes to food and water, which is our essential ingredients of maintaining life, they want them as low as possible, as when you ask the public. Now, what we're going to try to do at risk analysis in risk assessment here is to try to determine safety, the level of safety. What level of safety, what level of exposure, what are our risks of getting ill? Again, risk assessment is the process of estimating the probability that an event will occur and the magnitude of the adverse effect. Are you going to get ill? Are you going to get diarrhea? Are you going to drop dead? That's some of the part of the risk assessment. You can do those with microbial risk assessment as you can with most agents. Again, let me emphasize this word probability. We've been using that. That's gambling, basically. I always say gambling with germs, but it's like when you're playing the card game 21, you're always estimating your probability of winning or losing. And that's sort of the same thing we're looking at in a simplistic sense. But we're going to try to do it in a rather scientific fashion. Again, the risk analysis paradigm here, I just wanted to comment on a few things on here. What I'm going to really be talking about today is risk assessment. But as we already heard, risk management and risk communication are extremely critical here. Basically, if I look at a role here in the way we've been interacting, I look at myself as a risk assessor. I look at you people out there as risk managers and potentially risk communicators too. So I'm trying to give you basically the scientific basis to manage your operation in a better manner and to give you the tools, hopefully, to communicate to other people what these risks are. But you have to be very careful in the risk communication and develop that carefully, because you can create the opposite effect. So how do you relate risks to the general public that you're dealing with? I think the nuclear industry 30 years ago really failed in risk communication. I think it was one of the premier failures of it. They couldn't convince the people that they could build a safe nuclear plant. Why? I can tell you the classic reasons. I was sitting in an audience one time and the communicator up said, well, you're more likely to get struck by lightning, which was the wrong thing to compare it to, because everybody knows once in a while somebody gets struck by lightning, right? It's not the right thing to compare it to. In trying to communicate public health and sanitation, I always try to compare everything to the toilet seat, because everybody has figured out the toilet seat in their mind, right or wrong, is the dirtiest thing. So all I have to do is say, your desk has got 10,000 times more bacteria, even though they're not the same types of bacteria, we realize that, but it's a measure of cleanliness. The public can relate to the safety of a public restroom by the toilet seat or anything else. So a lot of things when you're dealing with risk communication is try to, how does the public receive cleanliness, and how do you associate degrees of cleanliness in the public's mind? You can do it very well with a professional like me to say, okay, there's 10,000 E. coli less, okay, E. coli, I got that. But the public thinks in a different manner, and it much more, not downgrading the public in any way, but in a more simplistic manner, because they're hit with a lot of risks that they have to make decisions on and decide which ones are really important to their family and which ones are not. You'd think the area I'm talking about is quantitative microbial risk assessment, or QRMA. This approach developed in the 1980s. It was, as pointed out previously, it's fairly new, and it's an approach that allows an expression of the risks in a quantitative numeric fashion. We try to do it in terms of infection, illness, or mortality. A lot of the regulatory people stop at infection because the probabilities of calculating illness and mortality depend a lot on the human individual, whether he's immunocompromised, whether we're dealing with an opportunistic infection. So usually it's easier to stop the regulatory process at infection. What I'm going to do with norovirus, though, because I think it's doable, is to go to the illness rate. Because when I can go to the illness rate, I can compare epidemiological data with my risk estimate. And I want to do that because I want to know how plausible this risk assessment is for setting standards for the cleaning industry. Now, I think we already heard this, but I want to give you, we can set standards. Government agencies set standards for microbial limits, for treatment performance. And I think with this industry, what is similar to what EPA did, rather than saying we will not have more than one norovirus in 1 million gallons of drinking water, what we're going to say is that you have to treat all drinking water in the United States to remove 99.99% of any noroviruses that might be there. Well, I'd like to use the word logs. Every log is a 90%, so 4 log removal. So every drinking water treatment plant in this country, regardless of where that water comes from, must remove 4 logs, because you don't always know what the concentrations are you're dealing with. And the same thing in the cleaning industry. And one way to utilize risk assessment to set standards is that we have a minimum level of a reduction of microorganisms, if that's our goal, or a radiochemical or what. In other words, and we're going to clean to remove 3 logs, because we know that will eliminate the probability we're going to have a waterborne disease outbreak or an outbreak related to a contamination on a surface event. So that's one way to look at the cleaning industry. And if you're working in a hospital, well, that has to be 5 logs, okay? If we're cleaning up after a outbreak of norovirus, we have to make that 6 logs. If we're dealing with a bioterrorist event, that's got to be 8 logs, because we can't accept the probability that we're going to cause an infection when there might be a high risk of mortality. So that's one way, just one way you might want to think about how you might want to use risk assessment in setting standards and guidelines in your industry. You can determine the cost benefits of treatment options. That's what I always like, because I've been involved more in the drinking water industry. So the question is, you want to build a $50 million water treatment plant if we're going to save $100 worth of diarrhea every year? A lot of people say yes, because if you're the one with the diarrhea, it's not pleasant. And Congress says, too, you can do cost benefits for regulatory thing, but that can't be your guiding principle either. You know, people, you can decide. But that's an advantage to me. In other words, is it worth spending a few extra bucks to clean better? How much more illness are we going to prevent? That's some of the things I think it's possible to do with risk assessment. And then applying technologies, you know, have different options of cleaning today, different technologies, different disinfectants. Using green clean, is green clean really achieving the same? It's a new technology. Through risk assessment, we can look at that. And compare relative risk between chemicals and microbes. That was an issue in the drinking water industry. In your industry, it might be where green comes in. Is it, you know, we have to accept that all chemicals may have some adverse effect, either respiratory, maybe certain types of illness, cancer, whatnot. We accept that in drinking water. We know that when we chlorinate drinking water, we're going to cause some cancer in the country, likely. That's what we're told. But the balance between microbial risk is so out of balance that we'll accept those risks. We'll accept a few hundred cases of maybe cancer from drinking water because we're going to save millions of lives. So that's one way of looking at it. And some of the interesting things you can do. Now, risk assessment and microbial risk assessment, it really has 4 basic steps. But what I want to do is go through with it, how we do it, and I'm going to go through with it with norovirus to see if I can come up with a standard for noroviruses. First, you got to identify the hazard. It's microbial specific, like salmonella. Or I think the example using MRSA is great because everybody knows with MRSA. I think MRSA is a major public health problem in the United States, so one could use MRSA. But you identify that organism. And then you have to have a dose response. How many organisms does it take to make you ill is what the really question is. And that changes with the probability. The more you're going to come in contact, the more you're going to get on your finger, the more you're going to put in your nose, the more likely you're going to get ill or infected from the organism. Now, fortunately, for a lot of enteric organisms, we have a lot of data on this. For most of the major enterics, we know what the dose response is. Unfortunately, for others, we don't. But we can make pretty good assumptions and maybe get to where we want with that. Exposure assessment. How much are you exposed to? If you look at risk assessment and do all the mathematical gyrations you want, it tells you this creates the greatest amount of uncertainty. Right here is the big unknown for us. We don't know what you're exposed to. How many microorganisms you pick up today in the toilet and put in your mouth? Okay, that's the big question. That's exposure assessment. Those are the things that people like me like to do. If you wonder why I spend so much time in the bathroom, I'm looking at you. Because this is the big unknown. Why is exposure assessment such a big uncertainty? One, it's the data-driven. We don't have a lot of data for the basic questions we like to ask. And also, the degree of uncertainty is huge. There could be one microorganism in that glass of water, or could be 10 million. And so that's a huge range of exposure that could potentially take place to an individual. So it creates a huge amount of uncertainty, orders of magnitude of uncertainty. The better I can define a number of organisms in your glass of water, the better I'll know what risk you're exposed to. Or same thing in a public facility, a public restroom. Let me go back to that. How clean it is can vary all over the range depending on the products you're using, how well it was cleaned, whether an individual in there came in there with one heck of a case of salmonellosis, I don't know. So it creates a great of uncertainty. And that's where most of the data that you're going to need is going to be in the exposure assessment. Risk characterization is where we put all of these diverse components together and we characterize the risk. In other words, my risk of getting salmonellosis today is 1 in 10,000 every time I walk into that bathroom, if I practice normal procedures going to the bathroom. So let me go through this again. I want to do it in a form that you can follow me because I'm going to do this several times as I go through this. You got to identify the pathogen. You got to determine the exposure, how you're exposed, the dose response data from human beings. You add that in there. Then you model the infection probability. This is a simple probabilistic model, and I'll talk to you a little bit more about that. And then you look at the clinical data. We know that not everybody who gets infected gets diseased. It can vary from only 1 person in 100 actually gets clinically ill to everybody, almost 99%. In enteric infections like salmonella, it's usually about 50% of the people will get ill that get infected. Why didn't the other 50%? And these are susceptible individuals. They're not already immune to it. Now, I'm only talking about people who are susceptible and non-immune individuals here. About why is that? I know they went to church on Sunday, you know, they They have natural immune processes going on. But I'll tell you, those 50% that didn't get ill, if I exposed them again, 50% of those would get ill. So it's a probabilistic game. The organism has to be swallowed correctly, it has to get through your stomach, has to find the right cells, has to start replicating. So it's always a gamble on the microorganism's part. But anyway, so the amount of clinical illness will vary a lot among people. And that's why a lot of people like to just look at the risk of infection, because sometimes this gets difficult depending on how virulent or how much likely it is to cause serious disease. And then you can predict, disease, mortality, death, almost every agent somebody dies from. So here's your dose response curve I talked about. This is a log dose. This is one organism, 10, 100, 1,000, 0.1 organism. And this is your probability. Look at this as a percentage. 20% of the people get ill, 40%, 60, 80%. In other words, with 10 rotaviruses here, about 75% of the people got infected, not ill in this case, sorry. With one organism, 15% got infected. And you notice the curve goes below 1. How can I go below 1? Well, you have to realize assay methods don't detect all the organisms. This is used as a cell culture method to measure rotaviruses. It only can pick up 1 in 100 viruses. So there are more out there than we can detect, but we can see that when we look at dose response. Now, this was done. You have to realize most of this work is done in medical students and graduate students, okay? So a lot of people say, are medical students and graduate students like the rest of us? I mean, they're all nerds, so maybe nerds are more susceptible to rotavirus infections. Does this dose response curve vary if your immune system is more suppressed, you're older, you're aged? Still a debate in my field. A lot of people feel the outcome is more adverse when you're older or you're immunocompromised, but the dose response curve does not change. Now, fortunately, and this is why probably, as I'll show you, microbial risk assessment does a pretty good job of predicting in a lot of situations because the data was developed in human beings. Unlike the chemical data, we didn't take a rat and exposed them. We took a human being and exposed them. And so the data is a lot more, although recent research indicates that the animal data correlates very well for most of the enteric agents with human beings. So apparently we can use animals. That's amazing what a student will do for a couple of bucks, always amazed. You look at that curve, and what do you get out of it? You get an equation. If you want a predictive equation, if I swallow a certain number of organisms, what's my probability of getting ill? And there's almost all microorganisms that have been studied to date fit either a beta Poisson or simple log normal, where alpha and beta really define the nature of this curve right here. The alpha and beta are defining this slope, basically, let's say. And P is your probability here. That's your odds of getting infected. N is the number of organisms you became exposed to, ingested, swallowed, got in your nose. The other is an exponential type, where R is, again, defining the nature of that curve. Very simple probabilistic models, and you can always get more sophisticated and do more in-depth statistical analysis if you want. But what I'm going to do is do what we call a point estimate. I'm going to estimate if you go into a room, what's your probability of getting a norovirus that's on the surfaces you're touching. Now, you can become more sophisticated and say, well, if you touch it, you get ill, then how is it going to spread? That would be a population model, and we want to look at everybody. But a lot of times in risk assessment, I find it much easier just to do the point estimate data in the analysis because it's less sophisticated. How good are these models? I mean, do they really work? Well, a little over a dozen years ago, Dr. Rose and Chuck Hawes and I looked at the data on salmonella outbreaks. One thing nice about foodborne outbreaks, you know how much people often eat, and it can quantify it. If you can quantify the exposure, which is how much people to eat, you can look at the predictions. And at this time, we looked at salmonella with water, and Packerton, it was given as, I think, a supplement or something, and then foods. And these were the attack rates that were observed. This is how the number of people that became ill, basically 100%. And then we looked at our predicted models. We were just hoping to come in with an order of magnitude, and we were amazed how close we could come to actually predicting the number of people who get ill. Now, since we did this work, other people have published on cryptosporidium in apple juice. There was an outbreak, E. coli in apple juice, where they knew how much the people consumed, and they were almost right on the money again. So we feel really confident that certainly when it comes to foods if we can validate these models. These models are not all hypothetical. And that's what I'm going to try to do today with the norovirus outbreak. We've been doing epidemiological studies and doing risk modeling at the same time to try to provide some validation for hard surface models and cleaning and disinfection. Again, redefining risk. What's an acceptable risk? Okay, this is the real question. What is acceptable? Well, EPA is the only one that really, in the World Health Organization, the only one who's come out and made recommendations. In the World Health Organization, the surface treatment rule for drinking water in the United States, they said drinking water in the United States has to be treated so that the risk of getting infected is 1 in 10,000. To say that maybe another way easier, if you have a population of 10,000 in a community, they're drinking water, only one of those people can become infected per year. EPA realized there's no such thing as zero risk, so they tried to set a standard. Where did they come up with the 1 in 10,000? Like most things, it was probably in a bar off of the mall, because these things seem to be hidden and are not really transparent enough. But roughly, they guessed that was your risk of getting waterborne disease in the United States, 1 in 10,000 per year. And they go that. Now, the risk, too, is per year. It's not per lifetime like chemical risks. It's per year is what they decided. That seemed to be reasonable. They didn't go beyond that. Now, the World Health Organization for drinking water said, well, maybe a risk in some countries would be 1 in 1,000 because they can't really achieve the level of drinking water we can in the United States. So they go, 1 in 1,000 maybe is okay, too. So those are two numbers we play with a lot. What should the real number be? You know, we usually use the 1 in 10,000 because EPA had enough nerve to come out with a number. And say that's an acceptable risk. So that's usually what I'm looking at as an acceptable risk. Now, how do we go through this? I'm going to go through it with cryptosporidium because EPA has done this for cryptosporidium a lot and changed their regulations and requirements for treating drinking water using cryptosporidium. I don't know if you remember, have you ever heard of the outbreak in Milwaukee where like 400,000 people got diarrhea and about 100 died in 1993? It was cryptosporidium because it was so extremely resistant to chlorine, chlorine couldn't kill it. So it had a big impact on the way we think about waterborne diseases in the United States. Basically, you have to look at what the concentration of oocysts in surface water are. All drinking water treatment plants of a certain size have to test their raw water every several years to find out how much is in their raw water. And then what you can do is determine the removal by the drinking water treatment process, how good, flocculation, filtration. We give 1 log credit for filtration, 2 logs for credit for or 1 log for filtration. You might want to think of it this way, like maybe cleaning with detergent X, we know we can remove 99% of the bacteria. Okay, but we want 99.9. So then you have to add a disinfectant to get that other 4 or 2 logs. So then 99.99 might be a requirement in some situations. But this is how the drinking water industry does it. You estimate the concentration in the treated water after you do it. One of the things the EPA decided it's too expensive and the volume of water we need here to assess the risk would be like 10,000 liters, 2,500 gallons, where you can test the raw water before you clean. It's a lot easier. There's a lot more there. You can do after. And we'll use simple tests like the coliform test or the fecal form test to make sure the treatment plan is working. Just like you've been talking about using ATP, that would be not a measure necessarily of your risk, but a measure of your ability to clean and achieve that 2 or 4 log reduction. We can say we achieved it in our clean plan. They do the same thing with drinking water, but they use microorganisms, or turbidity sometimes they use. And then we assume people drink 2 liters a day of drinking water. Just my comment, everybody goes, geez, 2 liters, maybe beer I could drink 2 liters a day. Okay, but drinking water. Why such a high number? Because the real number is more around a liter, is because if you want to protect 95% of the people, 95% of the people in the United States drink 2 liters of water or less. If I say, well, let's just average is 1 liter, right? If I make it 1 liter, then I'm only protecting half the people. And then I miss the susceptible, it goes like, nursing and women tend to drink more water. People in the arid Southwest drink more water. So there's a balance on what you look at that. Okay. And then you use those little equations I just talked about. What you can come up with something like this, you can go acceptable, unacceptable levels in your treatment process here. In other words, if you have 1 cryptosporidium per 100 liters of your raw water, you have to have at least 2 logs removal to get to that 1 in 10,000 risk. If you have more to start with, like 100 per 100 liters, you need 4 logs. One of the problems the drinking water industry ran into is conventional treatment only gets you to 3 logs, no matter how well you filter or flocculate that. And what EPA in recent rules has said, well, if you're going to have this high a level, then you have to add additional treatment. And what they do is they recommend like UV light or ozone to do the treatment. One of the things this industry could do is to do something like this is if we expect these high levels like an outbreak of disease, a terrorist event, our standards change and our requirements change of what we have to achieve. Or if we're in the healthcare professional, we use a different goal or set a different goal for our processes. But this is just what the drinking water industry. Let me go to Norovirus here, AKA the curse of the cruise ship lines. Our group has studied over 50 outbreaks on cruise ships. And in fact, if you're constipated, I could give you a recommendation of a cruise ship or two that seems to have more problems than others. So, we've studied a couple outbreaks in Las Vegas. The one thing I was going to point out, I never found a norovirus on a $2 chip, but I found them a lot on $5 chips. Maybe they don't even make those anymore, and there seems to be a selection for that. But and then I'm sorry, I always call them nosocomial infections, but they're not comical to the hospital arena. And then we've had a continuing problem on the Colorado River. There's rafting trips that go down every year, and people get norovirus on it. And it's tough going down a rapid trying to take a crap on a raft. You know, it's not the easiest thing you can do. So we get a lot of complaints. So we've been studying that group intensely. And then summer camps get closed. I mean, this is, when you talk about economics, we studied an outbreak at Northern Area University where a wrestling team was the focal point and it spread throughout the campus. And the Cardinals canceled their summer practice there. Cost this university, they canceled all their summer camps. Cost them millions of dollars. So it was a big economic concern for them. And dorms get them too, you know, you get dormitories outbreaks. So, I would say in terms of agents that are where the cleaning industry can really intervene at this time in history, norovirus and MRSA are the two where you can make your name when it comes to hygiene and cleaning, because those, to me, are two organisms that are out of control. What about norovirus? Steady increase in number of outbreaks and cases over the last years. 2006, 2007, worldwide were the largest number of cases ever reported, largest number of outbreaks in Japan and Europe ever recorded. A new strain evolved, well, one about 5 years ago and one more recently 2 years ago. Concern here, more people are susceptible than ever before to norovirus. And by the way, norovirus, like enteric infections, you can get as many times as you want. This immunity thing only goes so far. I mean, if you got immunity to diarrhea, you wouldn't have one by the time you were 12. But what they found out with norovirus, if you get it once, you can get it again as many times as you like on it, because immunity is very short-lived. But this new strain 2 years ago is more virulent. Instead of getting ill for 2 to 4 days, you get ill for several more days and you run a fever. Mortality is much higher with this agent. So microorganisms are getting more virulent. This is what norovirus looks like, Darth Vader's Death Star. It is the leading cause of non-bacterial gastroenteritis, probably causes 60% or more of all foodborne disease in the United States. Highly contagious. Doesn't take many to infect you. No long-term immunity. Susceptibility is related to blood group, interesting enough. If you're blood O, you get this more often than if you're blood group A. Far as we know right now, it only affects humans. High infectivity, the infectious dose 50, that's 50% of the people would get ill if I gave them 10 viruses. And it can survive for weeks on surfaces. Okay. We've been involved in a number of outbreaks here. We've been collecting epidemiological data. Just to show you how important it is in my own state, we have about 20 outbreaks per year. They do infect nursing homes, get hit a lot. Restaurants are being hit a lot with it too, for some reason in recent years. We studied houseboats because we had contained populations. We knew the people, we could get a hold of them. We were able to get into the houseboats and do environmental sampling. Because you can say, hold that houseboat for me till I get there. Where it's really hard to do that, somebody running out of a restaurant. And so we did rather detailed epidemiological investigation and went in there and we heavily sampled the fomites. Everybody knows what a fomite, right? They're not an alien from Star Trek. They're inanimate surfaces. You know, I'm sure all of you have a lot of fomite friends, right? People that don't move very much. What we were able to do is to get in there and sample these surfaces. We're doing molecular methods, so we look at genomes here. These are not gnomes. And nobody's really done this before, to try to get an idea quantitatively what we're looking at. Kitchen sink, where do you go to throw up, right? Okay, where do you go to wash your hands? door handles. And with this kind of information, I could estimate how many people might get ill in these houseboats, because now I know what they're being exposed to. Unfortunately, this method doesn't allow for viability of the organ testing, but I can make assumptions, I think, that are reasonable. What do you do when you go through this? Here's what we got to do. We look at the concentration on the fomites, loss of viability. We're going to assume that's 0 for this exercise. Transfer from fomites to fingertips. That's got to take place. Loss of virus viability on fingertips, transfer from fingertip to mouth, frequency of mouthing incidents, percentage of asymptomatic cases, and then I look at the probability of infection. Sounds like a really insurmountable task. However, there is data on this stuff. If you how much we know when you put a finger on a surface, you're going to touch 2 centimeters if you have average sized finger. Times you do this per day, we estimated 6. By observational studies of people in facilities of touching different surfaces, so we got a number on that. Number of mouthing events per incidence. There are studies on this. Actually, it comes out an individual alone. It's up to 18 per hour, in detail, but there's some work done at Berkeley on this, so we know how many times you stick your finger in your mouth, your nose, and scratch your butt if you really want to know. Percentage of asymptomatic cases, we know this from previous studies in that. It's going to be about 26 to 33%. There's been dose-response studies done with norovirus. Unfortunately, it hasn't been published, but I've been privy to the data, and it fits the rotavirus curve pretty well. So we use the rotavirus, which is one of the most infectious agents known, by the way. But norovirus from the human feedings data fits that same realm. The type of fomite, one of the things when we ran these models, I want to pass this on to because it's important in this industry, the thing that governed was transferability of your ability to pick it up on your finger and your ability to put it in your mouth. What we learned that stainless steel was far easier to pick a virus or a bacteria off stainless steel. We had students do this, touch this surface, and then we looked at how much they got on their finger, how much they put in their mouth. I'm sorry, I didn't say that. We did a lot of studies like that some years ago. Finger to mouth. But when you run the model here, and I'm not going to go into details of all the math, but I'm going to show you the results, is stainless steel came out the villain because you're more likely to pick it up. If you get it on a cloth, like this cloth table, I have 100-fold or 1,000-fold less in some cases, depending on the organism, of picking it up on my finger. But my odds are much better on this vinyl. So stainless steel, if you want to clean effectively, you got to go after the stainless steel if you have it in a facility, because that's where most of the transfer, it's going to drive a lot of the risk, interestingly enough. Moisture and other factors may play a role, though, too. Die-off on the skin seems to be rapid for some agent, which is a puzzle to us, but we only have one study ever done, so we need more data on that. And limited data on handshaking, and that I just put that in here. But we do have a lot relative to your industry. So what do? You run the model. It's really simple, Math 101. We look at the probability of infection on this when we looked at that data. Very high probability of infection because you're touching these surfaces 6 times a day. You've got tens of thousands of organisms on some of these surfaces. And every time you touch it, you have a probability of about 15% you're getting infected if your susceptibility. If you look at illness rates, it drops quite a bit, about 50 to 60, 49% is how you look at those numbers if you're getting actually infected. The observed attack rate on these boats was 50 to 87%. The model predicted 49 to 99%. What that tells me, everybody who was susceptible, some people probably may have existing immunity, or they're naturally immune to the agent, or they're a blood group A. We didn't get that information. It told me with this level that we saw there and them living in that houseboat for 6 days, that everybody probably who was susceptible got a dose enough to get infected with it. But we felt we were pretty good at this, comparing it to the epidemiology. Given the degree of exposure, it's likely that everybody became ill. Now, more recently, we've been looking at schools. We've done several studies in schools. This study was just published in the Journal of Pediatrics. Was looked at epidemiology study, looked at gastroenteritis disease in elementary schools. We studied compared classrooms which use disinfecting wipes at the end of each day and alcohol gel sanitizers. Less incidence of gastroenteritis in intervention classrooms, and fewer fomites contaminated with noroviruses and lower concentrations in those classrooms that practice proper disinfection. this is what you get when you look at classrooms. We collected this data for 3 months, and I do have the bacteriological data. I'm hoping maybe to develop some kind of correlation with bacteria and bacteria types in norovirus and cleanliness and cleaning in these studies with the database we got. I just picked it off the computer printout here just to show you the kind of data that we would get in this kind of study. Obviously, this is a control classroom here. This is one of them. You can see they do get norovirus during the SUSI. This is the classroom that did not use disinfectants on surfaces and did not use alcohol gel sanitizers. You can see the levels are much less than some of these other classes. I can't remember the total distribution because I just printed it out to give you an idea of what we're doing. This is per 100 square centimeters. What you're looking at here. So if you're looking at 1 square centimeter, you're looking at 6 viruses, or if you put a fingertip there, you might pick up 12 if you got a full transfer, or 6 if you got half transfer. Well, from this kind of information, though, I can do risk modeling and look at the probabilities of these kids getting ill and see if I can match it with the epidemiological data is really the goal here that we're after. Because I think it's really important to convince people who are in schools and that these schools are contaminated. This is only some of our data. We have a lot of data in schools now over the years. They are contaminated. Kids are picking up disease, and cleanliness does make a difference here. And so how am I going to use all this data? I'll go through the whole exercise looking at this school data again through all of these processes, and I make assumptions. One of the things in risk assessment, you always got to list your assumptions and your uncertainty, too. You can't be afraid to say, well, I could be off 100-fold in this. Okay, that may be true. But make them transparent. So I went through this exercise. Let's say that the goal here for cleaning is we want a risk of 1 in 10,000, just as a hypothetical number here. And we determine a one-time exposure that the doorknob is the only thing somebody's going to touch in, and the person before you had a norovirus infection and deposited it there. And the finger touches 2 square centimeters. 50% is transferred to the finger. We know that from studies on viruses that we've done. And 10% to the mouth. We've had people put their fingers in their mouth and seen how much gets in there. And then I can model the probability by those simple probabilistic models, and it comes out about 1 virus per square centimeter. So if that's your goal, you don't want any more than 1 norovirus per square centimeter. Now, the goal of the industry would probably try to determine, okay, what cleaning regime will achieve that? If I'm starting out, and if you look at this, the numbers in this classroom were as high as 60,000 per 100 square centimeters. We really got to get that down to 100 per 100 square centimeters. So what's going to do that? How effectively do we do that? Is our current cleaning procedures and that adequate to do that? How do we prevent cross-contamination? I don't have time to go into the norovirus outbreak in NAU, they actually ended up spreading the virus all over, but when they cleaned, because they didn't clean properly. So that's something the industry is going to have to deal with too. You can make it worse. Okay, you got to be careful. So this would be kind of one objective. One could do the same thing with MRSA and in other organisms. And that the goal of doing this is to show when I clean or use a certain cleaning product, procedure, whatever, I know I've reduced the risk to this level. Now, is this a reasonable goal, 1 in 10,000? I think so. I think the cleaning industry can do it. You can accept a higher level. If you get the levels too high, you're going to accept more illness, so it's a matter of rate. The other advantage we can do with this is, because I have the epidemiological data now, I have absenteeism data, I can give you a number how much money the schools might be saving is the reason for a lot of this stuff. But I think a lot of what we have to do is basically with the epidemiological data in the risk assessment is a ground truthing. Basically, like they look at satellites, they have people on the ground to make sure the satellite's seeing what's on the ground. It's the same thing with epidemiology. It allows me to look at the ground and see, am I really seeing the illness and rates I expected from my satellite of risk assessment? And that's what we really try to do. And hopefully I've given you some example of how this type of information might be used by your industry. Thanks a lot.